Welcome students. Today we are going to start a new chapter called as effective stress. This chapter is very important as far as civil engineering is concerned. This chapter has been brought up by the father of soil mechanics named Carl Terzaghi in late 19th century. Introducing this chapter called as the effective stress, the Mr. Carl Terzaghi has opened the floodgates, I would like to say, of many soil engineering problems, and therefore we can solve all the soil mechanics problems with greater accuracy. So, what do you mean by effective stress? We're going to study this point in this chapter. So as far as all of your competitive examination, or even if in case of the university examination, the problems are based typically in the evaluation of this effective stress and some theoretical concepts like its definition and its physical interpretation, so on and so forth. So we're going to see all this in detail. So let me start with the introduction first. So, as you're aware that the soil is multi-phase system. Multi-phase system means it consists of solids, it consists of water, and it consists of gaseous phase, which is air. So, that's what we have seen in the three-phase relationship. So remember, since it's a multi-phase, you have a kind of an interaction of this water along with the solid, and also the interaction with the solids with the air. So all these kinds of interaction play an important role once you apply a load onto the soil. So this kinds of interaction and how the soil will behave under the action of the load is truly be determined by these interactions. So as you are aware that if you take a very fine grained soil, suppose if I take a clay, so the clay has got a layer of water surrounding it. We call it as absorbed water. So this absorbed water, which plays a very important role, because the clay, as you're aware that the clay is formed by a chemical weathering, so therefore there is kind of a chemical interaction in between the water and the soil solid. There is a chemical interaction between the water, which is nothing but the absorbed water, and the minerals called as major mineral present in the soil is montmorillonite. Absolutely, we have three different minerals in the clay. We'll talk it about in later course of a time. We have montmorillonite, we have illite, and we have kaolinite. It is specifically been discussed in the clay mineralogy chapter. So this kind of interaction, which is specifically a chemical interaction, is very important, which governs the behavior of a soil under an application of the load. What do you mean by an effective stress? So, before introducing this chapter called as an effective stress, I would like to solve some of the mysteries in the soil mechanics. So, first mystery, or I'll tell first break point, is the introduction of the total stress. So as the name suggests, it is a total. It is a total. So if I take a soil, or if I take a container and I fill the soil, I fill the dry soil. Since I have filled a dry soil, so at the bottom of this container, if I consider a plane or section 1-1, at the bottom of this layer, the stresses acting which is nothing but the weight of a soil. Absolutely, it's a self weight of a soil divided by this cross sectional area A, this cross sectional area. And probably if I taken a cylinder, then probably it's a circular in plan which has a diameter D. So it becomes a total weight of the soil which you have placed in this container divided by the total area, which becomes the definition of the stress. We call it as total stress. It is a total. So this is sigma T, or just it is represented by capital sigma. And probably this total area in this case is nothing but the plan area of this. So therefore total area, if I take the cylinder, so it becomes equals to the pi by 4 into d square. That's all, pi by 4 into d square. Since in this case you know how much weight of a soil you're putting it in the container, but suppose I don't know the weight of the soil that I'm placing it in the container, and then how to determine this total stress. So for that, what I will do is I'll take the definition of gamma. Since I place the dry soil in a container, I'll consider definition of gamma D, which is nothing but a dry unit weight of a soil. So if I take if I know just the dry unit weight of a soil and I multiply by the volume of this cylinder, I will get the self weight of a soil, and divided by total area will gives you a total stress. So for this case, while determining a total stress sigma, I'll take the definition of gamma D, which is nothing but the unit weight, dry unit weight, into the volume of a cylinder. Volume of a cylinder is nothing but pi by 4 d square into height, up to which you have filled the dry soil, height, divided by the total area, which is pi by 4 into d square. So in this term pi by 4 d square, area will get cancelled, and you will end up at getting the total stress, which is nothing but gamma D into H. So remember, this is very important expression as far as the total chapter is concerned. So if you just came to know about the dry density or the unit weight, then you can evaluate just by multiplying with the depth of that layer. You can calculate the total stress. So it is very easy. So in practical purpose, what you are doing is that you are going it in the field, and you are digging the soil, you're taking the field measurements, and you will be evaluating this gamma D in field, and you're just multiplying this gamma D by H in order to calculate the total stress which is experienced at the level 1-1. So this is the first very simple case I have considered of the dry soil. But if I consider the complicated case of the water in between, then I'll bring one more, or I'll bring the definition of the neutral stress or pore water pressure. So since this is a very simple case I have considered, which is nothing but just the dry soil, so in the second case I consider the same example, but I'll add water in this container. The same container I'll take, same dry sand, and I'll pour it, and I'll pour the water in it. So once I started pouring water, its water level goes on increasing, and up to some depth which is absolutely visible. I consider the cylinder is to be transparent, is visible up to certain depth. So above this groundwater level we have the dry, and below it's a saturated soil. So if I just take the similar plane 1-1, So I will get the total stress, which includes the component of saturated weight as well as dry weight. So total stress in this case becomes gamma saturated into, if I consider this height as h2 and this height as h1. So this height as h2 and this height as h1. So it becomes gamma saturated into h2 plus gamma dry into h1. So this is how we have calculated the total stress. But here I have one more component which is called as a neutral stress or pore water pressure. So remember, even if you take a water, only a water, not in the soil. So if I just take a hypothetical case in a container, if I take a water, only water, and I consider a small element A at the bottom of a cube, then as you're aware of the Pascal's law, which states that in a water, even if you take any element, doesn't matter. That means if you take at bottom, if you take at anywhere or somewhere else, so this element has got the pressures all around it, and the pressure from all directions is equal. That's what the Pascal has told us. This is very famous law called as Pascal's law in the fluid mechanics, that probably you have studied it. So similarly, if you take the same law into consideration in this, so this pore water pressure, whatever I'm highlighting over here, is acting equally all around it. So therefore, by considering this law, the stresses are going to be same in all direction. So therefore, there is no as such a shear stress in the soil. So there is no component of the shear stress in the soil. So therefore, remember, a pore water pressure is a pressure which doesn't shear off the soil. So I will repeat again. So since this pressure, water pressure or a pore pressure, is acting equally in all direction, therefore there has not got the shear component of the stress. So therefore, this pore water pressure is not responsible for the shearing of the soil. So therefore, even if you place a water, even up to a full container, the soil is not going to fail. So therefore, soil still is in static case or static equilibrium, because the water is not shearing off the soil. But absolutely, this water component has to do with the total stress, because the total stress has got the two components. So one component of the total stress is the pore water pressure, and another component is nothing but very famous, which is nothing but the effective stress. So therefore, I bring a definition of effective stress on this slide. Total stress becomes equal to effective stress plus pore water pressure. So this is very important. We have got the two breakups of the total stress, which is made up of the two components. One is the pore water pressure and another one is effective stress. So if you have to determine this pore water pressure, it is very quite easier. Suppose I consider this level 1, and if I want to determine what will be the pore water pressure at the point or at the elevation of 1, it's very easy. So you just need to place the standpipe or piezometer at this section. So by placing a standpipe or piezometer, you'll get to know at how much level the water will be rising. So since the original water level is this one, the same water level will be maintained, because if there is a difference in between this water level and this water level, then absolutely the flow will going to occur. So since there is no difference in the water level, I consider this as a no flow condition. I'll write it over here. This level and this level is exactly same, so therefore this is no flow condition. So if there is a difference in point number 1 and point number 2, difference in this water level, absolutely, so So if there is a difference, there will be a head loss. So whenever there is a total head loss, the flow is going to occur. So if this level is this at the high level, then obviously the water will flow from high elevation to low elevation, so therefore water will be flowing like this in the upward direction. So if the water level is downwards, so that it means that the water will be flowing from this point to this point, because this is the length of the traversing, or this is the length under consideration in this case, and the difference is just the head loss, or the total head loss, delta H. Since there is a no head loss, so therefore this is specifically a no flow condition. So therefore, since it is rising up to a height equals to H2, I'll just use again the same principle, and I'll just multiply H2 with the unit weight of the water in order to calculate the pore water pressure, U. Pore water pressure is commonly denoted by a small u. Right, so which is very easy. So first we have seen how to determine total stress, and also we have seen how to determine a pore water pressure. So by evaluating total stress and pore water pressure, you can evaluate the effective stress. So just by deducting the pore water pressure from a total stress, you will get the effective stress. So remember, there is no way to measure a pore water there is no way to measure the effective stress. So effective stress cannot be measured, sigma dash cannot be measured. So I will like to highlight very important points in this concept of the effective stress. So first point is that it cannot be measured. Second point, effective stress is not a physical parameter. Effective stress is not a physical parameter. And third important case is that effective stress is not intergranular stress. Many of the research have claimed that the sigma is the intergranular stress, or sigma dash or the effective stress is intergranular stress, but it is not the intergranular stress. Intergranular stress is nothing but the stresses between the adjacent soil particles. If you have got such kinds of the particles, so if I consider this plane, so what is the stress acting in between the two particles at the contact area? So this is nothing but the intergranular stress. But remember, this intergranular stress is not the effective stress. In fact, it is something else. So we have seen the definitions of all the stresses. First we have seen total, then we have seen the pore water pressure, and finally we have seen the effective stress, and also we have seen how to evaluate the effective stress in case of the soil. We have seen evaluation of the effective stress in case of fully saturated soil samples, but in case of partially saturated soil sample, the procedure or formula is as follows. The effective stress is nothing but the total stress, obviously, minus pore air pressure plus some fraction into pore air pressure minus pore water pressure. So remember over here, because we have got the three phase, we have got air component as well. So if the air is exerting a pressure, or air is exerting a pressure once you apply a load, so that pressure which is exerted by the air is called as the pore air pressure. This is the fraction, this x is the fraction, and this again UW is pore water pressure. This fraction x, I would like to highlight, this fraction x is directly proportional to the degree of saturation, and the relationship is very easy. So X is directly proportional to degree of saturation SR. So if you got the dry soil, if you got a dry soil, that means degree of saturation is 0. You've got only then pore air pressure, and in that case the sigma dash will be equal to sigma into UA. But for evaluation point of view, you neglect the pore air pressure. But if it is given that this much air pressure is being exerted, then you need to take it into consideration in evaluating the effective stress. And if you got the degree of saturation equal to 100%, then probably X becomes equals to 1. And in first case, X becomes equal to 0. In second case, X becomes equal to 1, and therefore sigma dash becomes equal to just the normal formula of minus UA plus UA will get cancelled, so therefore it becomes sigma minus pore water pressure, which is equal to the effective stress. So this is just the fraction which accounts for the volume of voids filled with the water, so which again is related to the degree of saturation SR. So this is a formula of evaluating the pore water pressure, pore air pressure, and effective stress. And by this formula you can evaluate the effective stress in case the soil is partially saturated. In case of fully saturated, there is no need, so it is just the regular case. In case of fully saturated, just you need to deduct pore water pressure from the effective stress. So in case of the fully saturated soil sample, you just need to deduct the pore water pressure from the total stress in order to evaluate the effective stress. So this completes the concept of the effective stress, and we'll move ahead with the capillarity. Thank you.